Okay, so where we left off with was not here. It was way back here. We were looking at this question right here. There we go. So 18.5. So we finished A. With B, it's a similar thing to A in that there would be no rearrangement whatsoever. And so with B, so this one was A, and then for B, we'll put the same thing. So if we have our aromatic ring, it's going to react with the tert-butyl chloride, and aluminum chloride, and we're going to end up with tert-butyl benzene, which is going to look like this. Okay, so that one's done. So now with the last one, I'll just ask you guys, for the last one, with this alkyl halide, could that undergo a rearrangement? Yes or no? Could this undergo a rearrangement? Anybody have an idea about this one? It's a primary alkyl halide. Yes, absolutely it could. Absolutely. Okay, so what you're going to end up with is something like this. I'll try to scribble it on here. So if we have our aluminum chloride, so I'll just put AlCl3. We'll put in our lone pairs here. So what's going to happen is your Lewis base is going to react with your Lewis acid, and you're going to end up with something that looks like this, where we have the complex between the chlorine and the Lewis acid, so AlCl3. So this is going to be negative, this is going to be positive, but then we also have a proton here, okay? So it can react the way it's written, like this. So after your nucleophilic attack, you form the sigma complex, you do the proton transfer, you could end up with some of this compound. So I'll just draw the product of no rearrangement whatsoever, which would look like this, okay? However, it can also undergo a rearrangement. So I'll use my red pen here, where you're going to get a proton shift or a hydride shift like this, and then your electrophile would be this, where you have the positive charge here. And so, of course, after your nucleophilic attack, form the sigma complex, proton transfer, you would also end up with some of this compound. So you're going to end up with a mixture. Now, you don't have to give me any kind of statistics in terms of major or minor. All you have to know at this level is what are the products that are going to be formed, and these are the two products that are going to be formed. So you form the product from no rearrangement, and then you also form the product from the rearrangement. So in that particular case, you would end up with a mixture. So just remember that when you're dealing with Friedel-Crafts alkylation. And of course, you're going to have to practice this too, okay? You're going to have to go over this, a lot to get it all straightened out in your brain. So with that, you guys know the difference between an alkyl group, which is something like a methyl or an ethyl or a butyl or a tert-butyl and all those kinds of things. And then we can also have an acyl group, which is where we have a carbonyl followed by some kind of R group. So like a methyl ketone, that would be an acyl group, okay? So on and so forth. So now we're going to talk about Friedel-Crafts acylation. And if you don't remember this functional group here, this is called an acid chloride. So this has a name. It's called an acid chloride. So an acid chloride. And of course, there are 3 lone pairs on the chlorine, so it can act as a Lewis base and react with aluminum, which is the Lewis acid. And then you can see that all you're adding is this portion gets added to your aromatic ring like that. So this is a Friedel-Crafts acylation. So alkylation versus acylation. You've got to make sure you have the two straightened out. So when the acid chloride, so here is your acid chloride, when it reacts with your Lewis acid, which in this case is aluminum trichloride, you end up forming this intermediate, which then causes the leaving group to leave, and you form an acylium ion. And of course, you could draw a resonance form for this as well, the acylium ion. You could also draw this resonance form where you put the positive charge on the oxygen. And in fact, this one, the one that I just drew, would contribute more to the resonance hybrid because everything has an octet in the one that I drew, whereas in the one that's in green, the carbon does not have a complete octet. But the acylium ion is going to be very, very reactive. Okay, so here are the two resonance forms that I drew on the previous slide. But the bottom line is that this is a very strong or powerful, however you want to call it, electrophile, right? It's got a positive charge and it is ready to react. So if you put it in the presence of an aromatic ring, the aromatic ring is going to attack that electrophile. So here it is, the same old EAS mechanism, the same old electrophilic aromatic substitution mechanism. You get a nucleophilic attack by the aromatic ring. So you're starting with an aromatic ring. You have the nucleophilic attack on your acylium ion. So this is your acylium ion. Okay, you form your sigma complex, which of course is non-aromatic because it has an sp3 hybridized carbon in it. Then the proton transfer, you'll notice this is the same intermediate that was used in the chlorination reaction. Okay, so I know that you can hardly see everything on my slides, but you end up with your the proton transfer, which restores aromaticity. And then of course you would also form HCl, okay, plus you would regenerate your aluminum trichloride. So you'd regenerate your catalyst and it goes back into the reaction again. So there you go, Friedel-Crafts alkylation and now Friedel-Crafts acylation via the acylium ion. And so some alkyl groups, it turns out, cannot be attached to a Friedel-Crafts because of rearrangements, right? If we were to try to add, let's say we wanted to do this. Let's say we wanted to do benzene and then we wanted to react it with 1-chlorobutane. In that case, you're going to get a mixture of compounds, right? You're going to end up with the butyl benzene from no rearrangement. So 1, 2, 3, 4. But then you're also going to end up with the product of the rearrangement, which would be this. So 1, 2, 3, 4, like this. So you're going to end up with these two compounds. So you'd end up with butyl benzene and sex-butyl benzene. However, what if you only want to get the butyl benzene? Well, you can do it, okay, by a two-step process. The first step is to do your Friedel-Crafts acylation. So again, this step here is called acylation. So acylation. And of course, it's Friedel-Crafts. So anyhow, Friedel-Crafts acylation. And then after your acylation, you do what's called a Clemenson reduction. So this is a new reaction, okay? The Clemenson reduction is named after somebody. And the Clemenson reduction is using zinc and mercury. And you might be wondering about these brackets, okay? Zinc and mercury with HCl. And then we heat that up. So the zinc with the mercury in brackets, we call that an amalgam. Amalgam. Okay? And an amalgam is just a special type of mixture of zinc and mercury, which I'm not going to go into all the details of that. The book goes into a little bit more detail about it, but it's called a zinc mercury amalgam. Okay, so the amalgam, and what that does is it just burns off the carbonyl completely. So it just goes bye-bye. Okay, so once it was here, and now it's been reduced. Okay, so the reason it's called reduction is because now that carbon, instead of being bound to two oxygens or having two bonds to oxygen, it's got two bonds to hydrogen. So that's why it's called a reduction, right? Loss of oxygen, gain of hydrogen. So some other caveats with the Friedel-Crafts reaction. Next point is that polyacylation is generally doesn't happen. Okay, now why would this not happen? The reason why it happens with alkylation is because alkyl groups are electron donating, but acyl groups are electron withdrawing, right? I could draw a dipole this way. And so if this is pulling electron density out of the ring, that means the ring is going to be a weaker nucleophile. So as we go from here to here, we get the ring becomes less nucleophilic. So we'll put here less nucleophilic, okay, by virtue of that electron withdrawing group. So we don't get polyacylation, so don't worry about that. All right, question 18.8 just asks us whether each of the following compounds can be made using a Friedel-Crafts alkylation, or whether we should do an acylation followed by a Clemmensen reduction to avoid carbocation rearrangements. All right, so let's take a look at the first one. The first one, and I'll just kind of scribble some ideas here. So we want to add this group to the molecule, okay? So that means that we would need this alkyl halide, okay? So this would be our starting material. So 1, 2, 3, so you'd call this 1-chloro-2,2-dimethyl propane, I guess is what you would call this compound. However, we know that if you were to form a positive charge, right, on this carbon, okay, so let's just imagine you form that primary carbocation, that it's going to undergo some kind of rearrangement, okay, where you're going to get a methyl shifting. So you're going to get a methyl shifting over here like this, and then you're going to end up with something that looks like this, okay, where you can have a positive charge here. And so both of those are going to react. And so in that case, you would end up with a mixture of compounds. So we'd end up with a mixture in that case. So what does that mean? It means that we have to use the Clemmensen. So we'll write here, must use Clemmensen, the Clemmensen reduction. So we're going to do an acylation followed by the Clemmensen reduction. So what's that going to look like? Well, it's going to look like this. So we're going to start with our benzene. We're going to treat it with the necessary acyl or acid chloride. Okay, so this is the acid chloride we're going to use. We just put a carbonyl on here, okay? So then we need our Lewis acid, which is aluminum chloride. That's going to give us the acyl group. And then to remove the acyl group, we just do the Clemmensen reduction. So we use the zinc, mercury amalgam, and then HCl. And we heat that up. And I'm kind of running out of space here, so I'm just going to write product. Okay, that's going to give us the desired product. So what we'll do is we'll save B for our next class. So we'll put here, so we'll save this one for next class, and we'll take a look at this one then. So let's move on to the subject of an activating group. Now, I've actually kind of brought these up indirectly already in this class today. So if you remember, I talked about electron donating groups and electron withdrawing groups. So it says here, 2 issues arise when we're adding a group to the ring that already has 1 or more substituents. So let's say you want to nitrate toluene, right? You guys know the name of this compound is toluene. You had to memorize it in chapter 17. So if we do a nitration, the question is, you know, if we draw our toluene, okay, if we draw our toluene, where is the nitro group going to go? Is it going to go to carbon 1, 2, or 3? Which one of those positions is it going to go to? That's number 1. And then number 2 is, how fast is it going to occur? Is it going to be faster than the nitration of benzene or slower than the nitration of benzene? So the way you want to think about this is how good a nucleophile is methylbenzene, and then in terms of regioselectivity, where is the nitro group going to go? So let's take a look here. So again, there's 3 possible products. We could get the ortho, meta, or para. So that's one of the questions. And the other one is, how fast is the reaction going to go? Well, check it out here. It says the ortho and para products actually predominate. So somebody has done this experiment, okay? So they took toluene and they mixed it up with nitric acid and sulfuric acid that made the nitronium ion. So you have to remember that you form the nitronium ion, which is a super powerful electrophile. So I'm just scribbling it here just so we don't forget it, okay? And then we see that most of the nitration occurs at the ortho position, 63%. Some of it occurs at the para position, so it's about about half of that. And then there's like nothing in the meta position, okay? Nothing in the meta position. Well, it turns out that this nitration actually occurs about 25 times faster than it does with benzene. So I'm just going to scribble that out here. So I'm going to put 25, come on, 25 times faster than benzene. So this is a very, very fast reaction. Well, why would that be? Okay, well, first of all, let's take a look at the regioselectivity. All right, so somebody has drawn out all of the sigma complexes for the ortho attack, the meta attack, and the para attack. Now, what do you notice? There's nothing wrong with any of the structures that are drawn here with any of these sigma complexes. But if you draw the nucleophilic attack occurring at the ortho position, then what happens is you get a positive charge here, here, and here. Okay, and you see them shown here, here, and here in the sigma complexes. Well, what makes the one in the green box so special? Remember that a methyl group is an electron donating group, right? So it's going to dump electron density down in there. And so that sigma complex, that resonance form in the green box is going to be particularly stabilized. Why? Because the methyl group is dumping electron density into that positive carbon, that carbocation, which stabilizes it. When you have the attack occurring at the para position that's shown on the bottom, you notice that if you draw all three resonance contributors of the sigma complex, that one of them ends up with a positive charge also being adjacent to that methyl group, which is pouring electron density into that carbocation, which stabilizes it. With the meta attack, you see no such sigma complex. So that provides us with a rationale as to why the ortho nitration and the para nitration are the major products of this reaction. Now, in terms of the speed, why is it that it's so much faster than benzene? The reason why this reaction is faster is, again, because the methyl group is electron donating, so that makes the aromatic ring more nucleophilic. The pi electrons in the ring are more available for nucleophilic attack. All right. Now, in terms of your activation energies, okay, sometimes students like to see everything in graph form. So again, if we just look at the relative activation energies of ortho, meta, and para, you see that meta is much higher than ortho and para. Why? Because you don't end up with that resonance form where you have the positive charge adjacent to the electron donating group. You see, it doesn't happen when we have the meta attack. Give me a thumbs up if you're with me on the rationale here as to why we get ortho and meta is the preferred. Good. Okay, cool. All right, another thing that I'll say, and I don't think this is in the slides. Yes, it is in the slides, okay? Toluene is a bit of an anomaly. It's a little bit strange compared to everything, all the other electron donating groups. Why? Because a methyl group is very small, right? Methyl groups aren't very big, you know, respectively. So small. And since toluene, the methyl group is so small, it turns out that that is why you get more nitration occurring at the ortho position than the para position. There's two ortho positions and there's only one para position. So you might think it's in terms of the number of positions there are. Like there's twice as many ortho positions as there are para, so I should get twice as much. It's actually not because of that. It's because of the size of the methyl group. So as the groups get bigger, so if you go to ethylbenzene or isopropylbenzene or something, you're going to see more para than ortho because they're bigger, okay? So again, toluene is a bit of an anomaly, so it's kind of a funny place to start, but it's where the books always start, all right? So if you compare nitration of toluene with anisole, so you guys should know what anisole is. You had to memorize that in chapter 17. So anisole looks like this, so it's just methoxybenzene. Well, you can imagine that there's two effects from the oxygen, right? Oxygen is an electron, is the second most electronegative element in the whole periodic table. So you might think, well, this thing is really electron withdrawing, you know, by dipole. It is electron withdrawing via dipole. However, it's electron donating via resonance. Okay, it's electron donating. So there's kind of a battle between the two. Yes, it does have oxygen is electronegative. However, it turns out that the methoxy group actually activates the ring because the resonance takes precedence over the electronegativity. So we'll just put here we'll just put greater effect. The resonance has a greater effect than electronegativity. Electronegativity. Sorry, my Apple Pencil is like slower than what I'm writing, so it's kind of funny. So you see all the resonance forms here of anisole, where you can see that there's a negative charge here, here, and here in the ring. So obviously the oxygen does donate electron density, okay? So with that in mind, what that means is that the methoxy group just activates the ring so much that you don't even, it turns out that with anisole, you don't even need a Lewis acid. If you put it in the presence of a bunch of bromine, it just brominates the heck out of it. It just brominates everywhere, okay? So bromines go in positions 2, 4, and 6, right? This is position 2, 4, and 6. And if you're wondering why does it go to those positions again, it's because you have the negative charge at 2, 4, and 6, okay? So that's where the nucleophilic attack is going to occur from. So these groups that donate electron density, like a methyl group, or any alkyl group, or a methoxy group, like you see in anisole, we say that these are activators. And just like with the toluene, activators generally donate to the ortho and para positions. Okay, they don't donate, or sorry, they don't activate the meta positions. So now, if you look at the nitration of anisole, like we said, it's really fast. Okay, and it statistically occurs mostly at the para position, with some at the ortho position, and next to nothing at the meta position. So again, activating groups, where do they activate to? They activate to the ortho and para positions. With toluene, it gave you most of the product at the ortho position, but with any other group, and I mean anything else, it's going to give you most of the product at the para position. Why? Because there's free rotation around this sigma bond, which kind of sterically hinders these two positions, okay, the two ortho positions. So if you want to see the sigma complexes, there's a lot of information on here, but you can distill it down to the simplest possible bits. Whereas if you draw all of the resonance contributors after ortho attack, so this is ortho attack, you notice that you end up with one extra resonance structure. Same thing with para attack, we end up with one extra resonance structure that we don't have with meta attack, right? We don't get that extra resonance form. Maybe I'll just put an X there. We don't get it. And so since the sigma complex that's formed from ortho or para attack has an extra resonance contributor, it's more stable, it's got a lower activation energy, right? The methoxy group donates to the ortho and para position, so it kind of gives you the whole key there, right? If you look at the reaction coordinate diagram, you see the activation energy for the meta attack is much higher than for ortho and para. So what we'll do is we're going to save the deactivating groups for Friday. However, what I'd like you to try to do is to read the remainder of the chapter. So see if you can read the rest of chapter 18. And at a bare minimum, I would like you to read up to the point where you get to table 18.1, because everybody has to memorize table 18.1. There is rationale to table 18.1, but it separates the activating groups from the deactivating groups, right? Activating groups tend to donate to the ortho para position, and what we're going to see on Friday is that deactivators activate to the meta position. All right, so we'll still have a lot of content to cover on Friday.